We live in a digital age, and one of the promises, but also the perils of this age, is that so much data can be collected about our preferences based on the choices we make online. For instance, each time you buy something from Amazon or choose a movie on Netflix, you're telling these companies something about your preferences. And these companies can use this information to suggest something else that you might want to buy or another movie that you may want to watch. These are called recommender systems. And how do they make recommendations? Well, there are a lot of techniques, and there's much research going on to perfect these techniques these days. You might remember in 2006, the movie company Netflix announced a competition to find the best collaborative filtering algorithm that could beat its own algorithm. The competition lasted 3 years and attracted many thousands of entries. The winning entry improved Netflix's own algorithm by 10%. It, and many others, used matrix factorization methods like the singular value decomposition. The singular value decomposition has many important applications in data analysis, and in this lecture, I'll try to give you a sense of what it is and why it's so cool. This will build off many of the ideas we've encountered in this course so far. We spent a lot of time so far showing how linear algebra reveals hidden structure, and you've seen how useful eigenvectors and eigenvalues can be. But those ideas only make sense for square matrices. Is there some kind of structure theorem for non-square matrices? Recall that if a square matrix is diagonalizable, that means it can be factored as A equals P, D, P inverse, where P is an invertible matrix and D is a diagonal matrix. You can think of multiplication by P as performing a change of basis that takes a linear combination of the standard basis into a linear combination of the columns of P. So if A factors as the product of P, D, and P inverse, then the transformation of multiplication by A can be done in 3 steps. First, multiply by P inverse, which takes the basis of columns of P and transforms it into the standard bases along the axes. Next, you can multiply by D, and that just scales the standard basis vectors along the axes by the corresponding eigenvalues. And then, multiplying by P turns the standard basis vectors back into the basis given by the columns of P. A moment's reflection should reveal that this sequence of 3 operations will do the same thing as just taking the basis of columns of P and stretching them by factors which correspond to the eigenvalues. So to be diagonalizable means the transformation just looks like scaling in certain special directions. The scaling factors are the eigenvalues and the special directions are the eigenvectors, and these form the columns of P. A special case of this is when the matrix A is symmetric. We have seen that real symmetric matrices are diagonalizable, and in fact, the special directions in that case can be taken to be an orthonormal set. So then the columns of P are orthonormal, and the matrix is orthogonal. Then P inverse is just P transpose, revealing that any symmetric matrix A can be factored as A equals P, D, P transpose, where P is an orthogonal matrix and D is a diagonal matrix. But not every matrix is symmetric, much less diagonalizable. So it may come as a surprise that there is a standard factorization of any matrix A, even non-square ones, as a product of an orthogonal matrix, a diagonal matrix, and another orthogonal matrix. The catch is that the 2 orthogonal matrices are not necessarily inverses of one another. This factorization is called the singular value decomposition, or SVD, and it says that any m by n matrix A can be factored as U sigma V transpose, where sigma is an m by n diagonal matrix and U and V are orthogonal matrices of size m by m and n by n, respectively. The columns of U live in Rm and are called the left singular vectors, and the columns of V live in Rn and are called the right singular vectors. Diagonal entries of sigma are called the singular values of A and are ordered by size and denoted sigma 1, sigma 2, etc. And the singular values are always non-negative. Remember, sigma has the same dimension as the original matrix A, and so it's not necessarily square. When we say it's a diagonal matrix, we mean the only non-zero entries occur where the row and column numbers are the same. So a diagonal matrix could look like any of these matrices. The SVD also has some other properties that are quite cool. For instance, if the matrix A has rank R, then the first R columns of U will be a basis for the column space of A. And the first R columns of V, which are the rows of V transpose, will be a basis for the row space of A. And the last n minus R columns of V, which are the last n minus R rows of V transpose, will be a basis for the null space of A. Before we explain how to find the SVD, let's explain what it is geometrically. The geometric meaning of the SVD can be seen by looking at how a unit sphere in Rn gets transformed by the matrix A. Unit sphere means the sphere is of radius 1. And amazingly, it always gets sent to some kind of hollow or filled ellipsoid in Rm. It'll be a filled in or collapsed ellipsoid if the matrix rank R is strictly less than the dimension m. Remember that the rank of a matrix A is the dimension of its column space, and that's the subspace, that's the image of the linear transformation. For any ellipsoid, we can speak of the principal axes of the ellipsoid. This is a set of orthogonal axes along which the ellipsoid gets stretched. So to find it, look at the largest diameter of the ellipsoid, and that's called the major axis. Let's put that in our set. Then look at all the points in the ellipsoid perpendicular to this axis. It's another ellipsoid of one lower dimension. Find its major axis and put that in our set. Then look at all vectors perpendicular to the first two axes and find the next largest axis. Just continue in this fashion to obtain a collection of axes that are called principal axes. The so-called singular values of A are half the lengths of the principal axes. You can also think of them as the length of the semi-axes of the ellipsoid. And we usually order them from largest to smallest and label them sigma 1, sigma 2, etc. The matrix sigma in the SVD is an m by n matrix, which is all zeros except for the R non-zero entries along the diagonal of the matrix, where R is the rank of the matrix A. If you like, you can think of it as an m by n matrix with an R by R diagonal block D and every other block filled with zeros. For this reason, we call sigma diagonal even if it's not square. The diagonal elements of sigma are those singular values, and there will be R non-zero singular values if R is the rank of A. The columns of the matrix U represent the directions of the principal axes in the order from largest to smallest axes. And the columns of V are the unit vectors in Rn that map to the directions of the principal axes in the ellipsoid. Let's look at a pictorial example of a linear transformation from R2 to R2. And this will give us a feeling for what happens in general for linear transformations from Rn to Rm. Suppose that under multiplication by A, the unit circle gets transformed to some tilted ellipse. The vectors along the principal axes of this ellipse, scaled to length 1, are the left singular vectors. Their lengths are the singular values. For instance, the vector along the semi-major axis of the ellipse will be sigma 1, the largest singular value, times u1, the first left singular vector. Similarly, the vector along the semi-minor axis of this ellipse will be sigma 2 times the unit vector u2. These vectors along the axes of the ellipse, colored in green, were images of certain unit vectors in the domain, colored in blue. Those are the corresponding right singular vectors, which form the columns of V. And yes, it's funny that the left singular vectors appear in the right picture and the right singular vectors appear in the left picture, but that's because the vectors are named after the location in the factorization, since u is on the left and v is on the right. In higher dimensions, the left singular vectors would align with the principal axes of the ellipsoid, from largest to smallest. And if the linear transformation is doing some collapsing, or if its image doesn't span all of Rm, then some of the singular values will be 0. In such cases, there may not be unique choices for the singular vectors, but the singular values are uniquely defined. Now let's see how the SVD factorization works. We can visualize the factorization by enlarging our diagram to include 2 more pictures below the first 2. To say that the m by n matrix A factors into 3 parts means that, as a linear transformation acting on a vector in Rn and producing a vector in Rm, you can get exactly the same result by doing this 3-step process. First, multiplying the vector by V transpose on the left, then by sigma on the left, and then by U on the left. We'll indicate that in our diagram by an alternate path that goes from the first picture down to another picture, then across to another picture, and then up to the final picture. Look at the first map going down, which represents multiplication by V transpose. Recall that the matrix V represents the orthogonal transformation you get by rotating the standard basis vectors to the blue vectors in the first picture, which are the columns of V. Then V transpose, which is V inverse for orthogonal matrices, will rotate the blue vectors in the first picture into the standard basis in the bottom left picture. Then, multiplying by the diagonal matrix sigma just scales each axis direction by the corresponding singular value. So that turns the unit circle in the bottom left picture into an axis-aligned ellipse in the bottom right picture. And now we need another rotation that takes the standard basis to lie along the principal axes of the ellipse. And the matrix U does that. So that's the map going from the bottom right picture to the top right picture. So in the diagram, you see that performing the action of A on the top side of this diagram is the same as composing the 3 transformations along the sides and the bottom. Let's look at an example. The 2 by 2 matrix 1, 1, 0, 1 represents a transformation that's a shear. It takes a unit square to a sheared parallelogram. It's not a diagonalizable matrix because there's only one eigenspace direction, the vectors along the x-axis. You can see that under a shear, they do not change direction. But there are no other eigenspace directions because any other vector changes direction under the shear. What about the SVD? We'll show in a minute how to compute it, but here it is as computed by Wolfram Alpha using this command. And we obtain this. What do these numbers mean? Look at the effect of multiplying by the matrix A. Pictorially, it takes the square on the left to the parallelogram on the right. If we look at the unit circle under this shear transformation, it gets sent to the ellipse in this diagram. Now, the semi-major axis of this ellipsoid does not pass through 1, 1 as you might expect, even though the top of the circle gets sent there. Rather, the part that's stretched the most is just to the right of that, as indicated by the red arrow with a single arrowhead. Its length is 1.618. Yes, that turns out in this case to be the golden mean. The semi-minor axis of the ellipsoid has length 0.618. So the singular values of A are 1.618 and 0.618, and they appear in the matrix sigma. Now, the semi-major axis points in the direction of 1.6181, and if you normalize that, you get the first column of U. The semi-major axis turns out to be the image of the unit vector with a single arrowhead in the left picture. This is the first column of V. Similarly, the semi-minor axis points in the direction -1, 1.618, normalized, so this forms the second column of U. It is the image of a red vector with double arrowhead in the left picture, and that vector is the second column of V. You can check if you want that U and V really are orthogonal in this example, and these matrices actually do multiply to give the matrix A. Just remember to transpose the V before you multiply them together, because A is supposed to equal U sigma V transpose. Now we should say how we found this decomposition and then explore some of the great properties that it has. So, how do we compute the singular value decomposition? The key is to look at A transpose A. And the reason you might want to start here is that in the SVD we are searching for an orthogonal, a diagonal, and an orthogonal matrix, kind of like what we had for symmetric matrices. Though A is not symmetric, you can symmetrize it by multiplying it on the left by its own transpose. You'll notice that A transpose A is symmetric since its transpose is just itself. And it is a real matrix, so you can expect that it has an orthogonal diagonalization. So let's assume that A has an SVD, and let's see what that would imply about the factors. If A equaled some U times sigma times V transpose, then we can compute A transpose A, which involves first taking the transpose of U sigma V transpose, then multiplying that by U sigma V transpose. Doing the transpose thing, we get V sigma transpose U transpose U sigma V transpose. But U is orthogonal, so the middle terms U transpose times U is just the identity. So the product becomes V sigma transpose sigma V transpose. We've just shown that A transpose A is equal to V sigma transpose sigma V transpose. And this is very interesting because V transpose is supposed to be orthogonal. And sigma transpose sigma is a diagonal matrix because you can check its square and it's filled with dot products of the columns of sigma, and those columns of sigma were orthogonal. So V sigma transpose sigma V transpose is really an orthogonal diagonalization of A transpose A if an SVD exists. So this tells me what I should expect for an SVD. First, this says that the eigenvalues of A transpose A are the diagonal elements of sigma transpose sigma. But those are just the square of the singular values, sigma sub I. So the singular values of A should be the square root of the eigenvalues of A transpose A. Second, this suggests that V should be the matrix whose columns are the eigenvectors of A transpose A. And if you recall from our examples, the image of the columns of V under the transformation A should be the columns of U scaled by the singular value so that they lie along the image ellipsoid. So that means the columns of U should be 1 over sigma sub I times A times V sub I. We can summarize that here. Sigma is an m by n matrix and the same dimensions as A, filled with zeros except possibly for the diagonal elements, which are the singular values. Those singular values are found by taking the square root of the eigenvalues of A transpose A. Remember, there are n such eigenvalues since A transpose A is an n by n matrix. And you might be wondering why those eigenvalues are even real numbers or why they should be greater than or equal to 0. We'll answer that soon. The matrix V has columns V sub I, which will be eigenvectors of A transpose A, normalized to make them length 1. Now we know the V sub I are orthogonal because they were the eigenvectors of an orthogonally diagonalizable matrix. The matrix U has columns U sub I, which are 1 over sigma sub I, the ith singular value, times A times V sub I, the ith column of V, for the non-zero values of sigma sub I. Those other columns can be completed to form an orthonormal set. Now, why are the U sub I orthogonal? And why does U sigma V transpose equal A? We'll try to answer that. First, let's check. This theorem says the eigenvalues of A transpose A must be greater than or equal to 0. To see why this is true, suppose lambda is an eigenvalue of A transpose A. Then A transpose A times V equals lambda V for some non-zero eigenvector V. And we can scale V so that it's length 1 and it will still be an eigenvector. But now we're going to look at the quantity V transpose AV in two different ways. First, V transpose AV equals the product of AV transposed times AV, which you'll recognize as the dot product of AV with itself. So it has to be greater than or equal to 0. On the other hand, using the eigenvalue property, V transpose AV equals V transpose lambda V, which is lambda times the dot product of V with itself. And that dot product of V with itself is the square of the magnitude of V, which is 1. So this expression must just be equal to lambda. And together, these two statements show that lambda is greater than or equal to 0. End of proof. And so that actually helps us see why the singular values as the square root of these eigenvalues is possible to take, and it's real. Now let's check that the A times V sub I are orthogonal. We'll perform nearly a similar calculation to the one we just did. We'll take the dot product of A times V sub I with A times V sub j. If they are orthogonal, we should get 0. But the dot product of AVI transpose AVJ is VI transpose AVJ. But since Vj is an eigenvector of A transpose A, this simplifies to Vi transpose lambda j Vj. But that's just lambda j times the dot product of Vi and Vj. And since the V's were orthogonal, this will be 0 unless I equals j, in which case it will be lambda j. So that's what we claimed. Incidentally, it also shows when I equals j that the length of AVI is the square root of lambda I, which is just the singular value sigma I. So it tells us how to normalize AVI. So we can divide each AVI by sigma sub I to get U sub I, a column of U. From this discussion, it's easy to check that the matrix U times sigma is actually A times V, which shows that the SVD formula holds. Now let's do an example by going back to our matrix A equals 1, 1, 0, 1. To find its SVD, we'll compute A transpose A and find its eigenvectors and eigenvalues. A transpose A is easy to compute, and you'll find that it's 1, 1, 1, 2. Then, if you compute its eigenvalues, you find these. So the singular values are the square roots of them, which are 1.618 and 0.618. When you compute the eigenvectors, you'll find these. Once you normalize these vectors, these are the columns of V. Then we compute U by multiplying A times V and normalizing those columns. Doing this, you'll get this. Now, while software can do this now quite easily, it's helpful to know what's under the hood, and that's why we did these examples. Now let's see how the SVD can help us recommend movies to watch. Suppose we have 100 movies and I ask 500 people to rate these movies, including you and me. For now, we'll just assume that everybody has rated every movie. We can record this data in a 100 by 500 matrix, and each of us has a column in that matrix. What is the matrix doing? Well, you can think of it as a ratings map. You are a basis vector in a space of people that's 500-dimensional. The ratings map takes the space of people to a space of movies that's 100-dimensional. So your ratings are a 100-dimensional point in movie space. Each of the 500 people have their own point in moving space that record their ratings. This forms a cloud of points in movie space. And what can we learn about the shape of this cloud? Well, for one, the shape of this cloud may not fill out all of 100-dimensional space. Some people are similar to each other and preferences over movies are linked. People who like Star Wars may also like Indiana Jones. So then this cloud may lie to a smaller dimensional subspace of 100-dimensional space. It might be, say, R-dimensional. That subspace can be described by some basis with R things in it. And the SVD helps me identify the best R-dimensional subspace that describes the cloud and identifies R special basis attributes that could be associated with people and movies. For instance, a basis attribute could be something like comedy, action, or drama. And a movie could be a linear combination of these basis attributes. For instance, Star Wars is both action and drama. Okay, drama's debatable, I suppose. In any case, the cloud of points can help me make a prediction about how people will rate Star Wars if I know what linear combination of action and drama that movie is. Similarly, people can also be expressed in terms of their preferences for these basis attributes. I like action, but I do not like comedy. So I am an action movie watcher. That's an attribute of mine. There is some new basis in people space that may describe these attributes, like being an action movie watcher or a comedy movie watcher. So I can be expressed as some linear combination of action and comedy. I'd be positive on the action watcher axis and negative on the comedy watcher axis. The idea behind SVD is that we don't really know what attributes to look for in advance. The SVD does this for us. It first locates the attribute on which there is the widest variance in rating and makes that a basis attribute. This suggests a direction in movie space that makes the most difference in movie ratings. Thereafter, it locates the next basis element that's orthogonal to all the other basis attributes found so far, on which there is the widest variance in rating. These form the principal directions in which people are rating their movies. The SVD finds these basis attributes in movie space, but it also finds an orthogonal basis in people space, consisting of idealized movie watchers who only like movies with a singular attribute. The orthogonality of these bases means that the ideal attributes can be decoupled from each other. In other words, a form of diagonalization. So then the SVD factorization will tell us A, how much people like these attributes, that's V. B, how much movies have these attributes, that's U. And C, how important these attributes are to people's ratings of movies, Those are the singular values. Then we can make a prediction about a new person and how they will like a movie based where they sit in people space. We'll have to deal with some issues like what to do with missing entries in the matrix because, after all, we're trying to predict how people would respond to movies they haven't seen, and how to deal with these kinds of obstacles is an active area of research today and part of what went into the Netflix prize problem. The SVD also helps us throw away unimportant information. Recall that the singular values tell us how important various attributes are to the data I have gathered. If we arrange the singular values in order from largest to smallest, then if I throw away the smallest singular values, in other words, replace them by 0, then I may still have a very good approximation to the data. This gives us a way to extract only the most important information, which, for instance, could be important in smoothing data. Or we could compress data, like a photo, without losing too much information. For instance, if I have a photo, which can be thought of as a matrix of pixel intensities, and I perform the SVD on it and keep only the largest singular values, then we can see how much that changes the photo. What you see in these examples is a parameter that indicates how many singular values we are keeping. And you can also see that you don't have to keep too many singular values in order to retain a pretty good picture. What's going on when you throw away singular values is you're obtaining an approximation to A of lower rank. We're trying to find a subspace of the image space of the matrix A where most of the data lie. This is the key to compressing data. This rank K approximation of A actually turns out to be the best rank K approximation in a certain least square sense. So the SVD is a key tool in the arsenal for a data scientist to reduce the dimensionality of data. The singular value decomposition is a wonderful example of how many ideas from linear algebra combine to showcase both its beauty and its applicability.